Okay, so let's just jump into this. I want you to picture a number line, the standard one we all learned back in school. You've got 0, then 1, 2, 3, just marching off in a straight line. It's static. It's, honestly, it's kind of boring.
It's definitely the vanilla version of math, isn't it?
Yeah.
It works, but it hides all the messy, interesting stuff.
Exactly. And that is why today is going to be a bit of a mind bender. We are looking at a source material that completely flipped that whole idea on its head.
Yeah.
We're diving into a pretty dense research report. The title is Morphological Analysis of Recursive Prime Structures.
Which is a mouthful.
It is a huge mouthful, but the core idea is just fascinating. This report claims that integers, just, regular numbers, have a hidden geography. They have shape, they have movement, they have, and I can't believe I'm saying this about math, they have evolutionary paths.
It's a complete shift in perspective. Instead of a number being just a fixed dot on a line, this report treats them like dynamic systems. We're basically peeling back the skin to look at the clockwork inside. It's DNA, really.
And we have a very specific mission for this deep dive. We're not just talking abstractly. We're analyzing two specific integers. They are the protagonists of today's drama, 28,757 and 24,257.
Two numbers that, at a glance, they don't look all that special. Just a couple of 5-digit numbers.
Right. But we have a user who's been looking at these using the tools from the report, and they noticed these strange diverging patterns. And they asked a question that sounds, more philosophical than mathematical.
What was it?
Where's the journey going?
That is the perfect question to ask here. Because these numbers, as we're going to see, they aren't staying put. They are absolutely going somewhere.
So set the scene for us. The report splits these two into opposing teams. We have the negative subsystem, centered on 28,757, and the positive subsystem, centered on 24,257. Now, I have to stop you there. When I see negative and positive, I'm thinking minus signs and plus signs. But these are both positive numbers, so what gives?
Yeah, you have to kind of throw out the standard arithmetic definition for a minute. Negative and positive here, they don't mean less than or greater than 0. They refer to orientation.
Orientation, like spin.
Exactly like spin in physics. Or you could frame it as a study of order versus chaos. We have two distinct mathematical entities here. They look different, they act different, but as we're about to find out, they're locked in a very, very tight dance.
Okay, order versus chaos, I like that.
Not mine.
But to even see this dance, we need a special tool. The report talks about this thing they call the 36er Werkzeug.
The 36 tool.
Right, or the 36 modular grid.
And this is the crucial piece of, mathematical technology that makes all of this invisible stuff suddenly visible.
So how does it work? The source calls it a high-resolution sieve.
That's a great way to put it. Imagine you're looking at a beam of white light.
Right.
To your eye, it's just light. You can't see what it's made of.
Yeah.
But if you hold up a prism, a spectroscope, suddenly you see the rainbow. You see the hidden structure, the spectral lines. The 36 modular grid is that prism, but for numbers. Instead of looking at them on a line, we look at the modulo 36.
Modulo. Okay, that's a word that might bring back some high school math trauma. Let's break it down really simply.
It's actually pretty intuitive. Just think of a clock. A standard clock is modulo 12. If it's 1 o'clock and you add 12 hours, it's 1 o'clock again. You only care about the remainder.
Where the hand points.
Exactly.
Yeah.
Where does the hand point? Here, we're just doing that with the number 36. We divide a number by 36 and just look at what's left over.
And why 36? Is it a magic number?
In a way, yeah. It comes down to something called Euler's phi function.
Yeah.
And without getting bogged down in the math, what it tells us is that for the number 36, there are exactly 12 residue classes or pathways where prime numbers greater than 3 can actually exist.
So it's a filter.
Precisely. It filters the white noise of all the natural numbers and splits them into these 12 discrete channels. It organizes the chaos.
Okay, I'm with you. So we have this grid, we have these 12 channels. Now let's take our two numbers, 28,757 and 24,257, and run them through this prism. Because this is where the first aha moment happened for me.
This is the connection point. This is huge.
Right. Visually, the user said they look totally different. One's a spiral, one's a crystal. But when you look at the math in the report, let me just check my notes here. Okay, for 28,757, it's 798 times 36, plus a remainder of 29. And for 24,257, it's 673 times 36, plus a remainder of 29.
They both have a remainder of 29.
They're roommates.
They're phase locked. They live in the exact same residue class 29. And this is so important because it explains why we're even comparing them. They might act like strangers, but they're vibrating on the exact same frequency.
So if they're on the same channel, why do they act so differently? Let's cut them open and look at their factors. Let's start with the so-called negative system, number 28,757.
Let's do it. So 28,757 is a semi-prime, which just means it's made of two prime factors multiplied together. In this case, that's 149 and 193.
And the report points out that 149 is special.
It is. It's a Pythagorean prime, but what matters here in our grid is the spin it generates. When you take the residue of 149, which is 5, and you interact it with the residue of the other factor, the math creates a specific rotation.
And this rotation, this is what makes it negative.
Yes. The system defines this interaction as left-handed or counterclockwise. It's physically twisting the number sequence to the left.
Okay, so it's spiraling left, but the part that really blew my mind was the hunt. The report details this recursive factorization algorithm. It sounds terrifyingly technical.
It does.
But when I read the steps, it felt like a game of hot and cold, like a sonar pinging for something in the deep.
That's a great analogy.
Yeah.
It really is a hunt. The algorithm is designed to break the number down by subtracting these specific chunks, these terms, based on powers of 2. It's just chipping away to see what's left.
I want to walk through the sequence from the data because seeing it happen really helps. It feels alive. We start with our number, 28,757. The algorithm subtracts a massive chunk, 24,576.
Which is 3 times 2 to the power of 13. It's using its biggest drill bit first.
And we are left with 4,181. Okay, still big. So it subtracts the next chunk, 3,072. Now we're left with 1,109.
Still going?
Then it subtracts 768, and we're left with 341. It keeps getting smaller.
It knows what's happening. It's dynamically reducing the residue. It's searching. It's probing. It doesn't know the answer yet.
And then step 4, we have 341, and we subtract 192. And what lands on the table?
149.
The factor. It found it.
Exactly. The recursion discovers the prime factor 149. It hits what the report calls a null point, a point of resonance. The system chipped away all the noise and hit the fundamental frequency.
That is just so cool. It's like the number was hiding its factor and this thing hunted it down.
But look at the behavior it took to get there. The values were all over the place, 4181, 1109, 341. It's variable. It's moving. The report calls this system a mobile probe.
A mobile probe. That sounds like something from sci-fi.
It fits, though, right? Because it wanders. The full cycle for this system is something like 74 or 148 steps. It rotates very slowly, covering a huge amount of ground. It's an explorer, a seeker.
Okay, so that's the negative system, the searcher, the wanderer. Now let's pivot to the positive system, number 24,257. What makes this one so different, so stable?
Well, again, we break it down. Its factors are 127 and 191. And immediately, if you have any background in computer science, your ears probably just perked up at the number 127.
Why? What's the deal with 127?
127 is a Mersenne prime. It's equal to 2 to the power of 7 minus 1. Mersenne primes are like the rock stars of the binary world. They have this incredibly clean, rigid relationship with powers of 2. They are just fundamentally stable.
And since our hunt algorithm is based on powers of 2, that means 127 should behave very differently than 149 did.
Radically differently. If the negative system was a variable hunt, bouncing all over the place, the positive system is a standing wave.
The source calls it an anomaly. When I looked at the data for this one, it looked like a broken record. I honestly thought there was a typo in the report.
No typo. So let's look at the recursion for 24,257. It starts subtracting 12,288 minus 11,969.
And the result is negative 319.
Okay. Then the next step, 6,144 minus 5,825.
Negative 319. Again.
And it just keeps happening. It hits this constant difference of negative 319, and it just stays there. It stops searching. It locks in.
So wait, in the negative system, the algorithm landed on the factor 149. Here, it's stuck on negative 319. Is the machine jammed?
Oh, it's not jammed. It's vibrating. It means everything. The report shows this beautiful little bit of math. You take the final term in the sequence, which is 65, and you subtract that constant 319.
You get negative 254.
You divide that by 2.
Negative 127.
There it is. The factor.
Whoa! So it didn't find the factor by landing on it like a target. It found it by creating a stable vibration around it.
Perfectly put. Because 127 is a Mersenne prime, its cycle length, what the report calls the order of 2, is only 7. It's tiny.
So the negative system takes, what, 74 steps to turn around?
At least. And the positive system takes just 7. It's vibrating extremely fast, and that creates a rigid crystalline structure.
That is just a wild contrast. Okay, let's recap the characters. We have the negative system. It's spiraling, searching, Slow rotation, long cycle.
Mm.
And the positive system, it's vibrating, it's stable, fast cycle, locked in place.
The report calls the positive system the backbone. And for good reason. It holds the entire structure up.
Which brings us right back to the user's original question about the visual shape. They asked about a four-arm structure. They saw four arms radiating out on the graph and were confused.
And this is where we put it all together.
Yeah.
The user is seeing a superposition. It's like laying two transparencies on top of each other.
Okay.
You have the negative system, which generates two curved, spiraling arms because of that slow, wandering rotation.
Right.
Then you lay the positive system on top, which generates two straight, linear arms because of that Mersenne stability.
2 curved plus 2 straight equals 4.
Exactly. The visual difference the user saw is real. The curved arms are the chaos of the negative system. The straight arms are the order of the positive system. They're in the same channel, but they are shaping that space in completely different ways.
So we finally get to the big question. Where is the journey going? If these numbers get bigger and bigger, what happens to this four-armed thing?
This is the core prediction of the report. It uses a German phrase I love, entfernende Weiterentwicklung.
Which translates to divergent evolution.
Right, they start to separate topologically. Think about it. The positive system is anchored by that Mersenne prime. It's locked in. So as the numbers get huge, that system will just remain a stable, straight axis, a beam of light shooting through the number.
In the negative system, the wanderer.
It becomes ergodic, which is a fancy way of saying it's going to explore everywhere. Because it has that variable algorithm, as the numbers get larger, it's going to expand outwards into a diffuse cloud.
So visually, if we could fast forward 1 billion steps, what would we see?
You would see this sharp, crystalline needle in the center. That's the positive system. And spiraling around it, getting wider and wider, a diffuse, chaotic mist. That's the negative system.
The source uses a really powerful analogy. It says the whole structure looks like a DNA helix.
An asymmetrical DNA helix. That's the key part. One strand, the positive one, winds incredibly tightly and fast. Remember that 1:7 ratio, it's zipped up tight.
And the other one?
The other strand, the negative one, is winding loosely and so slowly, a 1:74 ratio.
So it's this lopsided, twisting ladder climbing to infinity. One side's holding on tight, the other side is just flapping in the wind.
That's a great way to put it. Mathematically, it's a structure built of two completely different timescales.
But here's my question. If they are drifting apart, if one's becoming a cloud, doesn't the whole thing eventually just snap?
Yeah. And that brings us to the safety valve. The report talks about null-Stellen 0 points.
I saw that, synchronization horizons. It sounds like something out of science fiction.
It kind of acts like it. Even though the systems are drifting, every once in a while, that chaotic negative system will hit a value that resonates perfectly with the positive system. Like, it might randomly hit that magic number, -319.
Oh, I see. So the wanderer accidentally bumps into the anchor.
It's not accidental, it's structural. These 0 points are moments where chaos and order align perfectly, and they prevent the whole system from scattering into complete entropy. They're like staples holding the DNA strands together.
So the journey, the destination, it isn't total chaos, and it isn't total rigid order either.
No. The final prediction is a state of coexistence. The journey leads to this complex structure where a crystalline backbone of order supports a massive, swirling cloud of chaotic potential. They need each other.
It's strangely beautiful. We started with two integers, 28,757 and 24,257. And now we see them as this dynamic duo. One is the searcher, the other is the anchor.
And they are locked in this phase-shifted dance for infinity. It really makes you rethink what a number even is. Is it a quantity or is it a process?
That's a deep thought. Before we wrap, I want to leave the listener with one final idea from the source. It suggests a direction for future research. It says, the key to finding order in all this chaos is finding more Mersenne-like islands.
Right. 127 was the key here. The question is, are there other stable backbones hiding out there in the billions or trillions? Are there other numbers that act as anchors in the storm?
That's something for you to think about next time you see a long string of digits. Is it a cloud? Is it a crystal? Or is it something completely new?
Look for the geometry behind the math. It's
Yep.
always there.
Exactly. Thanks for diving deep with us today.
It was a pleasure.
We'll catch you on the next one. Keep exploring.